Good morning. My name is Mohammed Samir. I'm going to be your SET physics tutor today. Today we have a very important lesson. We're going to talk about momentum and impulse. But first of all, I'd like to point out that I'm doing this video in the midst of the coronavirus situation. So we're all stuck at home. And so I kind of encourage you, just kind of, okay? I'm saying this to myself as well. I try to use this time to the best of your advantage. So if you want to work, if you want to, there's this project you've been wanting to do all day, all year long, but you've been like canceling it every day, procrastinating. Just stop, do the damn project, and get things done a bit. And so this is one of the projects that I wanted to do for a very long time, but because of the stresses of life, I've always canceled out. So I'm focused on this situation to try to be as positive as possible and make as many videos that will help you study for the SAT physics test as much as possible and assist you and guide you through the process. If you have any kind of questions, don't give up. The test is not that hard, but it's not that easy as well. So don't go there unprepared, and try as much as possible. Just go there for one time. And having taken the test myself, the SAT physics test is beautiful. The concepts are wonderful, but the secret is don't try to make stuff that you don't understand like stick out. So just work, constantly and directly. So let's get this started. Actually, let me get my chair in this fashion and get myself rested and positioned. So first things first, we're going to talk about momentum first, and then we're going to go into impulse. So what is momentum? Momentum is basically the mass times the velocity of an object. So what is the momentum of this car? How heavy is the car in kilograms? That's the mass, and that is going to be times velocity. What is its speed? So this way you have the momentum. Well, how is it measured? Kilogram meter per second. Okay, in this fashion, or newtons times second. Well, what do we use in momentum? Like we know the importance, we know the use of velocity, right? Velocity has a use. What's the use of momentum? Momentum is a measure of how easy it is to stop something. So we have a car, a small car, and the big car. Both of them have the same velocity. Which one is going to be easier to stop? The small car will be easier to stop. Why? It has a smaller mass and thus smaller momentum. So the smaller the momentum, the smaller it is to stop an object, and the larger a momentum, the harder it will be to stop an object. So momentum is always a measure of how easy it is to start stopping an object. Okay. So that is linear momentum. A total momentum is a quantity that you can actually work with, adding them and subtracting them, the various momentums that you may have. Did I say good morning? Good morning, good morning in advance. So we have the net momentum is equal to P1 momentum plus P2 momentum, and essentially just add or subtract. And we're going to work with these later on in the video, but there's one important thing that you have to take care of is that velocity. You have to maintain velocity, whether it's positive or whether it's negative. Well, what is a negative velocity? A negative velocity is a velocity that is moving in the negative direction. Well, what is the negative direction? I don't know. You decide. Or the problem on the test is sides. But essentially, if I'm saying that moving forward is positive and moving backward is negative, and you are moving backwards, your velocity, whatever it may be, I will put a negative value next to it. And so I will have a negative momentum because positive times negative is equal to negative. And so you can add these together and work with them as if they were scalar, as if they were. But it's always important. If you're ever asked on the test, is momentum a vector quantity? Hell yes, momentum is a vector quantity. Okay, So this is one of the points that are not very well explained on the test. Oh, I touched my eyes. I'm sorry. If you see a need to reduce the force during a collision, here's what you're going to do. What is force? Force is mass times acceleration, right? It's mass times acceleration. But what is acceleration? It's delta v divided by delta t, okay? So I'm just going to give a brief overview of what this is. It's change in velocity divided by change in time, right? Delta is change in. Delta is final minus initial. Change in, okay? So that is going to be delta v divided by delta t. That is equal to force, or you can say applied force. So what happens when delta t increase? When delta t increases, the overall force will decrease. Okay. So if you want to reduce the force acting during a collision, you will increase the elapsed time during that. Okay, that is essentially the explanation that has in the book. Okay. Now we move on to impulse. Now this is one of the very important lessons. Impulse is force times time. So what does this mean? When I have a car and I'm applying a force to this car and the car starts accelerating, starts moving, um, you just then give force in 1 second. You apply force over a time interval. And so impulse equals force times the time in which this force was acting. Okay? So I hit a car for 4 seconds with 100 newtons. 100 newtons times 4 seconds, 400. That is going to be my impulse. 400 newton times second. Okay? Okay, so now we move on. Now, do you see this text? I'm going to explain it algebraically. Okay? So get ready with your pen and paper. Now, momentum here is force times time, right? So what is force? We said m delta v divided by delta t times delta t. So force is this, delta t is that. Okay, now you notice something, delta t is up and delta t is down. So you can remove delta t's. So you'll end up with m delta v. Okay, impulse equals m delta v. Well, what is delta v? We said delta is change. And so m, so you remove delta v and say, what is change? How do you say change? You say vf minus vi, right? And so we will input the m in either side until we get mvf minus mvi. And so that's a momentum, right? And that's a momentum. And so what we can say is mvf minus mvi, that is called delta p. What is delta p? Change in momentum. And so impulse equals change in momentum equals delta p equals mvf minus mvi. That is the meaning of momentum. And so what people may do is confuse. They look at impulse and they say, oh, kilogram meter per second. They look at momentum. Oh, kilogram meter per second. And they say they're the same thing. Wrong. Wrong. Impulse is change in momentum. It is not momentum in itself. Because saying that impulse is momentum is a stupid thing. Because when you have a momentum, that doesn't mean the object is accelerating, right? You say mass times its current velocity, no acceleration. When you say impulse, you mean acceleration because there is a force acting. And with a force, you have acceleration. And so impulse equals change in momentum. Okay, hopefully that gets cleared out. Let's just erase everything here. So it's not stupid to make mistakes at first. Okay, it's not stupid at all. I'm just saying here for the purpose of the argument. Okay, so when an impulse acts on an object, the momentum of that object will change. And so this is just exactly what I said. Okay, that's delta p, that's pf minus pi, mvf minus vi, which is delta f delta t. Okay, and let's look at a problem here. Determine the change in momentum of a zero point 0.5 kilogram lump of clay striking a wall at 15 meters per second. So, they didn't say in the problem whether it moved. So I will assume the final velocity is zero. Okay, so df will equal zero. So it's given here. All right, thank you. And the initial velocity has been 15. I'll say initial velocity is 15. And so they need change in momentum. That is MBF minus MBI. Okay? Oh, let's start. BF minus MBI. So that is essentially being done here. And we find that the change in momentum equals negative 7.5 kilogram meter per second. Okay? So the negative sign in the answer indicates that the change in momentum. Oh, okay? So the negative sign here indicates that the change in momentum is opposite to the initial velocity. Okay, so the change actually happened opposite to where the ball was actually going. And so the minus sign may not appear in the available answer choices. So, you get the point. Make the most logical answer choice be your answer. Okay. Determine the change in momentum for a 0.5 kilogram rubber ball striking a wall at 15 meters per second. And so it didn't say whether it stopped or not. So here it said striking. Here, here it says striking as well. Well, this wouldn't be the case in the test. You'd always be given what's going to happen with the ball. So here they're doing a bad job on the books of saying what actually happens after the strike. Okay. Determine the change in momentum for a 0.5 kilogram rubber ball striking a wall at 15 meters per second. So we're assuming that the ball is going to hit and going to return with the same velocity here. And so the final velocity is going to be in the opposite direction, negative 15. And we're assuming it's returning with the same initial velocity. All right. But we're going to put negative sign because it's in the opposite direction. So it's going to be negative 15. So the magnitude of the velocity will be similar, but with a negative sign. So in that fashion, you will have the change in momentum. Mass is constant, but this is only on the SAT physics test. When you have complicated problems taking courses in engineering, you will have airplanes and you're supposed to find the change in momentum, but the mass is also decreasing as time is passing. So you're required to find the change in momentum of an object. That'll be the mass. You'll have final mass and the initial mass because you have fuel burn. Okay. So we move here to force ton graph. Okay. And so remember when we said that you could bring the area under a curve and make it equal something? Well, that is similar here. Force times time. Bringing the area is in a force ton graph is equal to the impulse. And so you'll just, here we have force is increasing, okay? Then it's decreasing. And what you'll do is just bring the area of whatever shape that you have, even if it's rectangular. That area is going to equal the impulse. And so here it says you can solve for impulse in a variety of ways. The change in momentum, the applied force multiplied by the elapsed time. These are the same thing, okay? The first and second are the same thing. And the final thing is the area under the curve. Okay, so here we have a problem that's pretty interesting problem here. The above graph illustrates the force acting on a 0.2 kilogram soccer ball as it is kicked. Determine the final speed of the ball. Well, we need to find the acceleration to bring the final speed. So what will we do? Let's see what the technique being used here is. Oh, the technique I'm going to use is different. Okay? And it's more intuitive. I like my techniques more than anyone else's. And so I'm going to bring the area. That is going to be 0.1, the base divided by 2, multiplied by the height. So, excuse me, I'm going to go out for my calculator. Well, can only be back in a very few short period of time. So we're going to go and divide 0.1 by 2, multiply that by 100, gives us impulse of 5. Okay, and so my technique would be multiply, divide, sorry, you have impulse is 5. What is impulse? That is force times time equals 5. I need to find the force. So I'll divide the 5 by time taken. So what is time taken? 0.1. So divide 5 by 0.1. I'm assuming that's going to be 50. There something. So yeah, it's 50. So the force is 50 newtons. Okay. What does force equal? That is mass times acceleration. So 50 equals the mass, which is 0.2 given in the problem. And the acceleration is unknown. So let's find the acceleration. So 50 divided by 0.2, acceleration is 250 meters per second. Woo. Okay, that's the acceleration. And we need the final speed. And we have first law of motion says Vf equals Vi plus at. So hopefully you understand this one. If you don't understand it, look for my videos. So initial velocity is 0, and acceleration times time. Well, 0.1 is the time. Multiply 250 by 0.1. That will get you 25 meters per second. The second way this was done here is we said the impulse when we brought the area is 5. Okay, and 5 would be units, of course. Newtons times seconds. Okay? Units are very important for this. And so we say, okay, mvf minus mvi equals 5, right? And so we say vf minus vi, we're going to divide both sides by the mass. So that is going to be 5 divided by 0.2. I'm going to go ahead and say that is going to be 25. I'm not very sure. Yeah, 25. So VF is, I don't know, VF is equal to minus 0 is equal to 25. And so this is the smartest way to solve the problem. My solution was a bit wrong because it took a long time. Try to take the least amount of time possible and follow this method instead of trying to find mine. So now we're moving here on the conservation of momentum. So there is this wonderful thing about momentum. It's always conserved. Okay, not always conserved, but excuse me, it's always conserved. Momentum has to be conserved. Uh, Let me give you this fun fact. If I push the wall behind me, I will actually increase the speed of the Earth, right? Yes, it's correct. But that will be very, very, very small values. Like, I think that would be smaller than a nanometer per second. But the thing is, there always has to be a change. There has to be a constant momentum. Momentum is the same. And so what does this mean? So you see all of this work. Okay, what is, like, we have these two boxes, these two objects. They're going to hit each other. Elastic collision. So they're just immediately going to hit each other. And they're gonna leave each other. So the momentum of the first object. Okay, where's my pen? Use a new color. It's going to be m1v1. The momentum of the second object is going to be m2 minus v2. And we said minus because it's moving in the opposite direction. I have determined on my problem that this is the positive direction. This is the negative direction. So any object moving in the negative direction will have a negative velocity. So this momentum plus that momentum, okay, is going to be equal. Now look at this. m1 plus v1i, okay? It's the initial velocity. This is initial. with initial meaning before the collision, and final meaning after the collision. So here, after they hit each other, they had like this cool hello brother meeting, and they left. We have m1 multiplied by negative. You're moving in the negative direction now. This object, this pops is moving in the negative direction now. So it's going to be negative v1 if, and everything here is going to be f because you already collided. So it's going to be plus m2 v2f. Um, so everything that was negative became positive. Okay. So I still haven't reached my point about the conservation of momentum. Okay. Now, what does the conservation of momentum mean? It means that the momentum before equals the momentum after. Delta pi, excuse me, sigma pi equals sigma pf. That self right over here equals that self right over there. Can you even believe it? Okay, it is wonderful about physics. It's sometimes the puzzle comes back to one piece and just one simple rule. Okay, the mass here, m1 v1 okay, plus m2 minus v2. Okay, and this is the initial, and so initial I will denote by a purple color, and the final I will denote by this color. So I will say initial here, sorry, and this is initial, equals the mass to m1 times the final velocity, which will be negative. This is not, I'm sorry, I'm gonna erase that. We're gonna see that later on. Okay, so here, this is way better put than I was trying to put it. So the initial momentum equals the final momentum. There has to be a conservation of momentum. What does that mean? The momentum before the collision equals the momentum after the collision. Well, what was the momentum before the collision? It was m1, we're here on this example, okay? m1 v1i, I because it's before the collision, plus m2 v2 minus v2 because it's in the opposite direction, and I because it's before the collision. Okay, this is the first part. After the collision, mass 1 multiplied by negative v1 f because it's already collided. Here, we're hitting each other, we're leaving. Plus mass 2 times v2f. And notice here, v2 was negative, now it's became positive. There's been a change in direction. Hopefully you understand that. So now we move on to inelastic collisions. Well, before we move on to inelastic collisions, there's a point I want to add here. This very small point. When I have a gun, I really don't want to own a gun. Okay, and so this gun, it's a very weird version of a gun. What happens when I have a bullet? An explosion occurs, okay, between the bullet and the gun, and I'm not very familiar with gun terminology, but the bullet will explode. No, excuse me. The back end of the bullet will explode, and the bullet will increase its trajectory forward. Okay. So there is actually a conservation of momentum. The mass of the gun. I'm not going to write this. I'm just going to say it, and I need you to do this with your pen. The mass of the gun times the velocity of the gun before the collision. So that is 0. The gun has mass, but the velocity is 0. So mass times 0 is 0. Plus the mass of the small bullet, okay, times the velocity of the small bullet, 0. Okay, equals the mass of the gun, okay, times the final velocity. Well, that is the velocity moving backward. Have you ever noticed in movies when someone hits the gun goes backward? And so the bullet goes forward, the gun goes backward. Hopefully, please don't make memes on my recreation here. But the gun returns backward because it has rebound. You know, there has to be conservation of momentum. The bullet moves forward, the gun has to move backward. Okay, and so M1. Let me write this again. I don't care about the time. Okay, the mass of the gun times the velocity of the gun before the collision plus mass of the bullet times the velocity of the bullet before moving. Okay. Okay. So stop. After collision equal. Okay. The mass of the gun times the velocity of the gun after the collision. GF. Well, well, what is happening right now? The gun is going to recoil at a speed plus mass of the bullet. That is going to be a very high. It's very small, but it will be very fast. So the velocity of the bullet after. So EF and VF, and hopefully you're not laughing right now. Okay, so the bullet is moving forward with a velocity that is really high, and so when you equal that out, you can find many things that you want to know. You can find what will happen to the speed of the bullet, and so the heavier you make the gun, the heavier you make the gun, the less recoil you will have. Okay, the less hurt you will be. If you have a very small paper gun and you like shoot a big bullet, that could kill you. That can hit you really bad. But I'm being optimistic. Hopefully, you're not going to use the gun, so that's why I'm being optimistic. Inelastic collisions. Inelastic collisions involve two objects that collide and stick, and they will stick to each other. So the first example we take is they hit, they leave. No, this is going to be an example where we have a static object or moving. It doesn't matter. But what matters is they will hit each other, and there will be one dominant object that will take the other object with it and move with it. So we have a truck, 10,000 kilograms, moving at 3 meters per second. This is exciting stuff, and it's going to hit a 5,000 kilogram car that's going to move it along. What is the resulting speed of the railroad freight cars after the collision? They will have the same speed because they will stick to each other. That is the meaning of elastic and inelastic. Okay, inelastic collisions involve two objects that collide and stick together. Inelastic collisions, not necessarily. No, they will bounce off each other. Okay? Okay. So now we move on to inelastic collision. Inelastic collision. So the mass. Okay, let me write this. Okay. That's exciting stuff. The mass before the collision, 10,000 kilograms. Don't look here. Look with me. Okay, 10,000 times the initial speed of 3 plus, well, you have to bring the momentum of the other vehicle. 5,000 times 0, stopped, equals, after the collision, after they hit each other, they have the same mass. Okay, look at this rule. M1v1 plus M2v2, they will move with each other. They have added mass, so you will add their mass. 10,000 plus 5,000, I think 15,000. So that will be 15,000 times final velocity. They're moving with the same speed, of course. And so you calculate this, okay? You move the numbers around, you find the velocity that will move by. This is the easiest kind of problem. You have a big car hits a small car. The big car has this mass moving with this speed. The small car is at stop, at rest. They hit each other. What happens? The small object may be moving. I don't know, but the conservation of momentum is always true. Okay, so if you see collisions or explosions, conservation of momentum. In every single case in the world, there is always conservation of momentum. Like, always. Can't run away from that fact. As long as they're touching each other. Now we move on to explosions. Now, explosions are very important uh, important part. So explosions, you have a mass. This mass explodes, right? Well, you will bring M1. So what's being assumed here is you have two masses, and these two masses will leave. Just two, it could be billions, but we have a simplified explanation here. M1 plus M2 times initial velocity, which is going to be zero. Okay, it's zero because before the collision, no particle has any velocity. So we assume that m1 plus m2 times vi, which is going to be zero, well, that is going to equal zero, equals, now here we're going to have, okay, m1 multiplied by v1, uh, final after the collision, plus m2 times v2. And of course, you're going to have a very complicated problem, but hopefully we're in the SAT physics program, so it's not complicated at all. Because in a real bomb, you have particles not just going on the x and y axis, they're going everywhere. So you have upstairs, downstairs, north, south, east, northeast, and so you won't have to deal with that at all. So don't worry about it. Explosions, just understand how that conservation of momentum in the both in the three situations that we had. Okay. Energy in collisions. So I'm just gonna just teach this part, and then I'll make a quick summary of conservation of momentum. Um, Now notice that kinetic energy during collisions is not conserved because it will convert into other things. Two cars hit each other. Okay. So the initial kinetic energy will not equal the final kinetic energy. The final kinetic energy will be less. Why? Because you had kinetic energy converted into heat. So touch the cars, they're so hot. Into sound, but that sound is not for free. Okay. Um, so you have lots and lots of conversions, actually, friction and that's heat. Okay. All the other stuff. So kinetic energy is not conserved and it becomes thermal energy and sound energy as well. And so initial kinetic energy minus the lost, okay, minus the lost kinetic energy will equal the final kinetic energy. And they're saying one and two, they're assuming that two objects hit each other. This is how you bring, just in case you don't know, kinetic energy is equal half mv squared. Okay. Um, and finally, last but not least, they are perfectly elastic collisions. And in perfectly elastic collisions, there's no like very minimal sound. There is no heat transfer at all. Like they hit each other. Excuse me, no heat generation. Heat generation. So they hit each other. They leave. No kinetic energy loss. In this case, initial kinetic energy of them both equal kinetic energy of them both because the kinetic energy lost is equal to zero. Okay, so let me activate the whiteboard. Okay, okay. So there are three things that we have to consider here. Use red. There are three kinds of collisions, okay, that we have taken, and this will be our last part. Um, the first collision is called, oh, I don't like that. How do I make this bigger? No, 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 no. It's called inelastic collision. So what happens in an inelastic position? We have two objects. Hit each other, and then one of them dominates, takes the other with it. So you get this weird shape. They take each other, and they move forward. And so you will say, all right. And most cases, the other object will be stationary, meaning stopped. Okay, so you'll say, we'll call this M1, we will call this M2. Let's use the this one. So I will say M1 times v1 plus m2 times v2, which is going to be 0, okay, because it's stopped, no v2, equals m1 plus m2, because now they're moving as one piece, times the final velocity vf. Okay, this is in the first position and situation. Now we move on to the second position and situation. Oh, I finally found the big pen. Hey, yes, is elastic collisions. Now these objects are going to hit each other, and when they do hit each other, they are going to bounce back. Please keep in mind, always, 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 always keep in mind that there is always a direction, positive, and there is negative, okay? In the last example, I didn't say positive and negative. I'm sorry, all right? So you have an object that is going to the backward, you say negative, and then you say positive, okay? So hopefully I'm going to try to make it easier in this example. So the object is moving here in the positive direction. So we'll call this M1 and call this M2. And so M1 times V1 plus M2 times negative V2, you know, it will be a negative value, okay? If you are given in the test, the velocity of mass 2 is negative 50. Don't say negative 50. I'm going to go crazy if someone does that. It's going in the opposite direction. It has to be a negative value. So you just have to keep in mind the direction. And so that will equal M2 times V2. And so it's now that we have, excuse me, just going to undo that. It's wrong. Move on with the same order. M1 times negative V1, because the object is going backward, plus M2 times V2, because now the object is moving in the opposite direction. And so in this way, you know, these were two situations that we understood how we work with momentum. I think there was a third situation that I might have forgotten, and so I'm going to erase that. Let's go to the share of this. Go there. Okay. Yes. And in the bomb example, sorry, I may have forgotten that. Okay. In the bomb example, you have two bombs, just one bomb, sorry, that exploded. So the initial velocity is 0. So let's say we have two particles that will explode, M1, M2. And so they are both, it's essentially the same mass, right? Okay. Look here. They're the same mass. So M1 plus M2 times the initial velocity, which is 0, equals, okay, back to the board. M1 plus M2 times 0 will equal the velocity of the first object, M1 V1, plus final object. This is after the collision. So boom, now boom. This is before, this is after. So MV1 plus M of negative V2. This one is moving. I said this is positive. Is that a problem? That's not a problem, okay? And I said this is negative, so I'm saying negative V2. Okay, so I think that is it. Where is the screen? Oh, I'm going to turn off the share. Okay, no share. Hey, where am I? Excuse me, I get a bit confused these days. So with the rise of technology and everything. Well, you need to see me. Okay, so I just guess this is going to be it. Thank you very much for watching my videos. I am forever grateful. Study hard, work well for the SET physics program, and goodbye. Oh, here it is.